mechanics. And all good mechanics starts with our friend Newton and his laws of motion. And there's the first one. Of course it is in Latin because that's how Newton wrote them. He wrote them in Latin. Corpus omni preservari in statu sui crescendi vel movendi uniformate nisi quatenus e viribus impressis cogitur statum illum maturi. For those of you who don't understand Latin, okay, so this is the first one. Everybody continues in a state of rest or in uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. We just work as straight lines. Straight lines are just easier to work with, and that's what they're talking about with a right line, straight line. And what I'm saying is this: if I'm here standing still, nothing's going to change unless some forces, someone pushes me in the back, whatever, and then I'll move. But the same deal is if I'm moving uniformly, nothing's going to change unless someone goes, "Hey, stop!" puts a force in. That's all the first one say. The second one's probably the most famous of them all. Motus proportionalium. There we go. What is it saying? The change of motion is proportional to the motive force impressed, and it is made in the direction of the right line in which that force is impressed. In other words, in a straight line. What? So motive force is proportional to the change in motion. Force is proportional, change in motion, change in velocity, acceleration. Force is proportional. We know when things are directly proportional, they're equal to some constant times that thing, and the beautiful thing about it is that constant is just simply mass. So force is equal to mass times acceleration. I say the more famous of the three laws is that one. That brings me to the third one, actionia contrarium, which is probably one of the more misquoted laws of them all, often called quoted as, for every action there's an equal and opposite reaction. Yeah, okay, that's sort of what he was saying, but this is what it really is saying. To every action there is always opposed and equal reaction, or the mutual actions of two bodies upon each other are always equal and directed in contrary parts. Forces balance. Okay, essentially that's what that's saying. Forces balance. Vectors and forces then. Forces are vectors. When we're working with forces, we're essentially working with vectors. So all that work we've done on vectors comes in handy. We like to work in straight lines. And ideally, horizontal and vertical is very nice because we've got our x-axis, we've got our y-axis, things like that. And that's where the idea of resolving any force into just those directions. It doesn't have to be horizontal and vertical, of course, just two directions which are perpendicular to each other. That's all we really want to do. The original force, I say, that will end up being then the hypotenuse of a right angle triangle. So we have these things, resultant vectors, which we know. And the resultant vector is just the sum of all its components. It's the result of all the other things. Something like this. We're going to find the magnitude and direction of the resultant force. We've got a force of 3 newtons acting at 60 degrees, 5 newtons acting at 15 degrees, and we want to know what it is. So, all right, there they are. Well, the result of those two are the two vectors added together. So there's the red one. It's not actually a force, it's the result of the other forces. Okay, so that's the result of all the forces. And I can find I can find the size of it. I can just use the cosine rule on that triangle. I can play around with geometry and go, well, yep, there it is. I've got that. I could find the direction. Again, I could use the sine rule because I could find theta, which then would allow me to find the direction, which is going to be 60 minus theta. But that can be a hassle. So this is why we project it into horizontal and vertical. We can make the question a little bit easier for ourselves. So this force of 3 newtons, I can say, well, that would be the equivalent of going up and then across. And I could do the same thing with the 5 newton one. And so I could rewrite this, not with the actual forces that are there, but with the result of all the forces. I know I'm going to have one force which is going up, and it would be 3 sine 60, and the other one 5 sine 15. It's always going to be the hypotenuse, 3, and then I always just look at the angle and say, well, am I looking at the opposite or the adjacent side? And then I know whether I'm talking about cosine or sine. So 3 sine 60, 5 sine 15. And then going horizontally, I've got 3 cos 60 and 5 cos 15. So I could create this new vector. And here's the new triangle. That's a lot easier than using the cosine rule on the sine rule, because it's just Pythagoras' theorem and then a simple trig function, or tan. I can work out the angle as well. So by Pythagoras I can get the resultant force, 7.43, and the angle, there it is, 32.59. So I guess that illustrates why we break things up into components, essentially just to make life easier for ourselves. So what are all the different types of forces that we could encounter? Resistive forces. So whenever a body moves in a medium, I don't know why they call it a medium, it could be in air, in water, whatever, it's subjected to a resistive force, and it always acts in the opposite direction to the motion. Newton's third law. There's always going to be a balance. I'm pulling back the other way. The resistance is proportional to the power of the velocity. It's usually v or v squared, and what it tends to be is for low speeds, v, but once the speed gets higher, it's v squared. You don't really need to panic about that, because they'll probably tell you in the question which one it's going to be. You don't have to make the decision, oh, am I going to use v or am I going to use v squared? So it will usually be one of those two things. Gravitational forces, also called weight. The force of attraction of the object from the, Earth, if we're on this planet, or any planet, it's called the force of gravity. Gravity is not a force. Gravity is an acceleration. The force is the force due to gravity. And that's what we call weight. And so using Newton's second law, we know that'll be mass times acceleration. So it's mg. Forces are paired up. Again, back to Newton's third law. If A exerts a force on B, then B exerts a force on A. They pair up. Going to have the same magnitude, but they'll be opposite in direction. Normal contact forces. These are the interesting ones. So whenever an object is in contact with a surface, there's a force on that object at right angles to that surface. It's why right now I'm able to stand here and my knees are not buckling. Because if the only force acting on me in the vertical direction was gravity, my knees would be buckling right now, because I'll be wanting to, but there's not. Because there's this other force that the ground, if you like, is imposing on me, going in the opposite direction with a force equal in value to gravity, and it counteracts it, and I can stand quite nicely. It's the same reason why you're sitting there right now, but you don't feel like you have to fall through the chair, because gravity would make you want to go through the chair, but there is a force on that chair acting on you so that you're not going through the chair. It balances out. So normal contact force, or sometimes we just call it the normal force. Frictional forces. So whenever we're moving across a surface, there's friction. There is a resistance there. Otherwise we'd just go, whee, and off we'd go. It wouldn't stop. Frictional force does have a limiting value, so a force that it can't exceed. Again, it will act in the opposite direction to motion, because it's a resistive force, so it's always in the opposite direction to which you're travelling. And it's a constant, so a coefficient if you like, of the normal contact force. That'll always be that. But again, you don't have to worry about that, because they will usually tell you this is what it'll be, or something like that. Tension are the other big ones. Tension forces. When you have a light string, I love how we always say a light string. I guess the main reason it's a light string is because if the string was really heavy, then the mass of the string itself would then affect the motion as well. So we say, a light string. So in other words, the mass is, we can ignore the mass. I guess is the easiest way to explain that one. An object attached to a string is going to have this force equal in magnitude at either ends of that string. And it always is directed away from the object that you're working with. Always away from it. That's what we call tension. Do not think up has to be positive and to the right has to be positive. You can define positive to be any direction that you wish. It's just that once you've decided that, you've got to stick with it for the problem. You can't just go changing it. And usually the most convenient way to do it is whichever direction I'm travelling in, I will make that positive. And in that way, resistance will always be negative. And the thing I know you hate, everyone hates, draw yourself a diagram. I don't care how simple the problem is. Just draw a diagram to get a feel for what's going on here. Where are the forces going? A heavy box, 32 kilograms. It's got a handle on one side. Two people are trying to move it across the floor. One's going to pull it horizontally with a force of 20 newtons. The other's going to push it with 25 newtons, but despite all that, the box doesn't move. Draw a diagram of all the forces acting on the box. And often for these objects, we just put a little dot. Sometimes we call them Bob, good old Bob. There's Bob. There's our box that's going to move. Well, not move in this case. What forces do we have? Okay, I've got this first force. I'm going to pull it with 20. Someone else is pushing it with 25. I'm defining that direction as I'm moving. There's my positive. But because I'm moving something along the ground, there'll be a resistive force of friction. Now, there's a third force happening. There is, of course, force due to gravity on the object, but it's in contact with the surface, so there would also be a normal force. So there's actually 5 different forces. Now, you may not need to use all of them. A lot of the times, these vertical forces we don't even have to consider because they're just going to balance each other out. They're irrelevant. Not all the time, but a lot of the time. Find the frictional force. So now I'm saying, all right, I want to know what the result is. So I've got this new thing. It's not a force. I don't put it on my diagram because it's not a force. It's the result of all the forces. And force is mass times acceleration. So I've just defined the direction to be x. We love x as a pronumeral. It's going to be sum of all the forces. So what do I know? All the forces are. The result of all the forces, I'm defining the direction I'm moving to be positive, will be F1 plus F2 minus F3. But I know it's not moving. So the result of all these forces is 0. It's like I'm stationary. It's like there's no force being applied at all. So the result of all of that is 0. Therefore, 0 is 20 plus 25 minus F3. F3 was my friction. Okay. Friction's 45 newtons. Got 2 trucks here. One on the left, 30 kilograms. They must be toy trucks, hey? Yeah, 30 kilograms. A big truck is going to be there. And the one on the right has mass 50 kilograms. We know the truck on the right's pulled with a force of 120 newtons. The one on the left is connected by a chain. Well, a chain, a string, it's just joining the two things together, and there's going to be tension in that. And look, they've only put the horizontal forces on there because in this particular problem, again, the vertical forces are irrelevant. We're not going to use them. Just look at each truck individually, and then we will link the problem together with the thing that links the trucks together, that being the chain. So I'm just looking at the left-hand truck, and I'm only interested in horizontal forces. So I have tension going to the right. What other horizontal force do I have? None. So the resultant force on that is simply going to be equal to whatever that tension is on that truck. But I know the mass of the truck is 30, so I know 30 times its acceleration will be t. Okay, I can get an expression for acceleration. Now let's go to our truck on the right-hand side. The right-hand side, I have tension, but it's going to the left, and I have this force of 120 going to the right. So its resultant force is 120 minus t. Notice I changed the pronumeral because they're different trucks. Mass of that one is 50, but it will have the same acceleration because it is acting as one system, so they'll move with the same acceleration. So I now know 50A is 120 minus t. The tension becomes the linking of this problem, or does it? Actually, no. It's the acceleration in this case that's going to link the two together because it's the tension that I want to find. But essentially, we're just saying, hey, I've got simultaneous equations here. Solve the simultaneous equations. And if we solve our simultaneous equations, we get t is 45. Let's make it even more fun. A mass of 2 kilograms is now resting on a smooth plane inclined at 30 degrees to the horizontal. It's connected by a mass of 4 kilograms by a light elastic string, which passes over a small pulley. Now it looks something like that. Draw a force diagram. Okay. all the forces that are happening here. My 2 kilogram object here is in contact with a surface, so there'll be a normal force, but it's at right angles to the surface, so it's going that way. There would be a force due to gravity. Now, just because it's sitting on an incline doesn't change gravity. Gravity always acts directly down, so that's 2G. Over on my other one, I'm going to have 4G gravity working on that one. But then we're joined by this string. There will be tension going away from the object. It will be the same value because it's the same string. They're not different strings. So for the 4 kilogram object, it also has tension, but it's going up the string. Now, I think for this we're ignoring friction. Technically, it also has friction once it starts moving because it's sliding along. So sometimes they'll tell you to ignore friction, sometimes you have to put it into the problem. Again, we're going to find the tension in the string if the 4 kilogram block is moving down. That would mean our 2 kilogram block ends up moving up the slope because this one's moving down. Let's look at the 2 objects individually. The 4 kilogram mass. I don't really need to consider anything horizontally on the 4 kilogram mass. Hang on, that's the one that was going down. Yeah. Because it's purely vertical motion. I don't need to worry about anything horizontally. So what's happening vertically? Well, gravity, 4G, was going down and tension was going up. That's all that was happening on that object. So I'm saying, my notation here, R is sort of saying the resultant force on the 4 kilogram block. I know the result of all those is 4G minus T. Remember, it's moving down, so I'm defining down to be positive for this problem. So 4G minus T. But force is mass times acceleration, so for this one, 4A is 4G minus T. Okay, let's go look at the other block. Ooh, much more interesting. Yes, I could resolve this into vertical and horizontal and give myself a much more difficult problem as far as manipulation. Remember, all I said was, no, they just have to be at 90 degrees to each other. And the tension is at 90 degrees to the normal force. So if I just consider in the direction of tension, then I don't have to worry about the normal force, because it's got nothing to do with what's happening along the plane. So that's what I'll do. I will resolve it that way. Let's draw gravity now. Gravity is going to break into 2 components. But to get that equivalent gravity, I would go down the plane and then at right angles to the plane to get there. There'd be my 2 vectors. Well, I need to work out where the angle is. Bit of geometry, we can work out that angle there would be the 30 degrees. Okay. Forces up the plane. I'm defining up to be positive because remember our mass that was going down, we said it was going down. So we have defined that to be positive. And if that's going down, then my 2 kilogram block is going up the plane. So I'm going up the plane is going to be positive. Just got to be consistent. So I've got tension going up the plane, but then I have this component. It must be 2G sine 30. The hypotenuse is 2G. It's opposite the angle I've labelled as 30 degrees. So it's going to be 2G sine 30. Its resultant then will be the tension minus the resistance there of 2G sine 30. And it will also be mass times acceleration, but this time it's 2 times A. Again, we now have a link between the two. We've got simultaneous equations. We're trying to find T. Well, I'll go back over here. 4A must be double my answer on the right hand side because that was 2A. I got 4G minus T is 2T minus 4G sine 30. Rearranging all that. There's my answer for tension, but we can do some calculation. I've assumed G is 9.8 for this one, I think, to get that answer. And again, sometimes they'll tell you, use 9.8. Sometimes they might make life easy for you and go, let's assume G is 10, whatever. But I've used 9.8. If they don't tell me, I'm usually going to use 9.8 for questions like this.